Hello. We have discussed several aspects of calculus of variations and its applications in mechanics and some in structural optimization. Today, to cap it all, we are going to discuss variational framework for structural optimization of structures that involve other domains such as electrical, electrostatic, magnetic and other things. We will just take two examples, one from dynamics which will not have other domains, but other one will have domains from electrical and thermal involving the structural mechanics, just to show that variational methods are very general and we can apply to a number of situations. Okay. So, let us start with how a structure can be done under the dynamic conditions. So, let us take the example of what we call dynamic compliance that we want to minimize for a structure. What we mean by that is that if we have a structure, let us say a bar, we would like to minimize its strain energy not under static conditions, which we have already done, but we will do it under dynamic conditions. So, if I have a bar, okay, which will not be, what we want to design is actually its cross section. So, if this is the axis of the bar, let us say that there is a load P which earlier was just a function of x, x being this coordinate with x equal to 0 here and x equal to L here. P is a function of x, it varies from point to point along the axis of the bar, but it is also a function of time. What kind of function we do not know, just like we do not know what kind of function it is in terms of x, just p x t is given to us. Now, we would like to make it stiff under dynamic conditions, because the fact that this is a function of time tells us that when the load changes a function of time, the structural deformation that u that we have, axial deformation, that will also be a function of time. Okay. So, what we would like to minimize now to make it stiff under dynamic condition is to minimize integral over L, we will say P u dx. Okay. But since P and u are both varying with x and time, we would do an integral over certain time also, some capital T is given to us and put dt. Okay. So, this one we can call MC dyn, meaning that MC dyn, okay, let us define here. What we would like to minimize is MC dyn is what we call dynamic compliance. Okay. We want to minimize this. If you minimize this dynamic compliance, minimization of MC dyn implies stiffest, because we are doing an optimum, stiffest structure under dynamic loading, under dynamic loading. That is what we will have. Okay. We like to do this subject to, and what is our variable? It is a of x. We will write the constraint. First, let us discuss what this a of x is that we have been using. That will be the cross section profile of the beam. Okay. That change is a of x, changing area, that is our design variable or optimization variable. Okay. Now, we have to write the constraints. For the constraints, we have now a dynamic situation. So, we need to have a function that controls this u x of t. Okay, that is a state variable now, which is a function of x and time, right. So, we will write this as E A u prime prime plus p that we have. Okay. Though that was the equation that we had for statics. Now, we would also have rho A u double dot equal to 0. Okay. So, we are now the constraint that we have governing equation is for dynamics, because we have included the acceleration rho A u double dot is there, and then we will also have the volume constraint as usual 0 to L A dx, that volume should be less than V star that is specified. Again, remember that whenever we have a function type constraint, the corresponding Lagrange multiplier is going to be a function of x, and here the time also, just like this equation is. This equation is valid for all values of x, all values of time. So, this will be a function of lambda will be a function of x and t. This capital lambda will just be a scalar, because this is a functional type constraint. Okay. Again, let us remind ourselves that this is functional or global constraint, and this is a function or local constraint. Okay. And we should also complete the problem by indicating what is given, what is data, that here loading is given, we assume, and the length of the bar is given, time over which we want to consider optimization capital T is given, Young's modulus is given, rho is given, and V star is given. Okay. These are all the things that are known. Now, how do we solve the problem? The first step of doing it, as always, is to write the Lagrangian. Okay. So, we would do that. Looking at the problem, let me write the Lagrangian. So, we will have the objective function 0 to L, 0 to T, Pu, and then we have all of this lambda times, I will expand this E A prime u prime plus E A u double prime plus P plus rho A u double dot and plus capital lambda A, all of this dx dt minus lambda V star. Okay, that is just a constant, last one we do not have to worry about it. Okay, this is lambda V star. Okay. Now, if you see we have put dx dt, whereas the integral here for the this constraint is only for up to dx, there is no dt. So, it is safe to divide by, so that when you do integral over time, that t gets cancelled, although it does not really matter a whole lot. Once we have that, we notice what our integrand is, that is our integrand f, for which we write our, or rather Euler Lagrange equations, Euler Lagrange equations. So, here we have f and t. So, when you take variation, we have to take into account that things are varying with space and time. So, when you have two independent variables, how do we do it? We write the equations as first there will be, if I take first of all variation of the Lagrangian with respect to area of cross section, okay, and that would imply dou f by dou a minus dou f by well, it will be d by dx of dou f by dou a prime plus d square by, we do not have that actually, a double prime is not there. So, this term is not needed, but instead we have the time. So, we have d by dt of dou f by dou a dot, okay, that is also not there. So, it does not matter. So, a has only a and a prime. So, that is all we would have, and we equate it to 0. That gives us the what we call design equation. And that is in this case wherever a is in okay, let me just underline, a is here, yeah, those, and then a is also here. So, I can write this equation dou f by dou a as lambda e u double prime, and we have rho lambda u double dot plus lambda, all this is for a, minus dou f by dou a prime, that. So, we have that here. So, that will become minus e, a will not be there because we are taking with respect to a prime, e a lambda u prime prime equal to 0, which we can simplify a little bit. So, we have lambda e u double prime plus rho lambda u double dot plus lambda, and this, if I expand the last term, that will be e lambda prime u prime minus e lambda u double prime equal to 0. So, now this term and this term cancel. So, what we get is rho lambda u double dot plus capital lambda minus e lambda prime u prime equal to 0. Okay. That turns out to be our design equation. So, now if we write the variation with respect to u and equate it to 0, we get the adjoint equation. Okay. Now, we got the design equation, we need to write the adjoint equation, and I see that I forgot this t, that will be lambda by t does not change much, it is just that the t that we introduced here, because the constraint was only, this constraint was only having dx, when we brought it, since we have both of them, I just put t, so that when you do integration with respect to t, that t will cancel and we will get the constraint as it is, okay, the volume constraint, small change. Now, for u, we have u there, u prime, u double prime and u double dot, right. So, we have to write this as dou f by dou u minus d by dx or dou by dou x, same thing, dou f by dou u prime minus d by dt of dou f by dou u dot, which we do not have, plus d square by dx square by of dou f by dou u double prime plus d square by dx dt square, not dx square, dt square of dou f by dou u double dot equal to 0. Okay. Let us work it out. This implies u is there, that is u. So, that is the only place u is alone, that will be p dou f by dou u, and then we have dou f by dou u prime that is over here, and that is it. So, that gives us lambda E A prime, since u prime prime d by dx, and u double dot is not the 0, is not there. So, that this will be 0. And then we have the next one, that is u double prime is over here. So, that will give us lambda E A double prime, because we have d square by dx square, plus we have the double dot term, that will be lambda rho A. Yeah, that is it, but this will be double dot, meaning d square by dt square, okay, that is equal to 0. That is equal to 0. Now, let us simplify it, this adjoint equation. So, we want to see that it will be similar to the governing equation. So, what we will do is, we will not expand this, because this is going to get cancelled with something. That is, if I expand this, okay, that is going to give lambda prime E A prime plus lambda E A prime prime plus rho and A do not vary with rho and A do not vary with time. So, double dot will only be, second derivative will only be lambda dot double dot equal to 0. Now, we see that this and this get cancelled. So, what I get here is P plus lambda prime E A prime plus rho A lambda double dot equal to 0. This is our adjoint equation. And if you notice, the governing equation that we had, which is E A u prime, I will just dash line, this is our governing equation. E A u prime prime plus P plus rho A u double dot equal to 0 is how we got it. Okay. So, that was also just like this, wherever lambda was, it was u. So, this was our equilibrium equation. So, we can conclude from these two that lambda is equal to u, lambda x t is equal to u x t. We substitute this back in the design equation, we get rho u u double dot plus lambda by t minus E u prime square equal to 0. That is what we get. So, once you know u, you can compute u prime, and then we will say what lambda is. Then we can use optimal criteria method to solve this problem. Okay. So, adjoint equation can be easily solved. All right. So, the same setup that we had for static problem also came from dynamic problem, but there will be a small change if we consider damping term. Okay. Damping term in the governing equation, let us say we add that. So, I will write the equation that we have P u prime E A u prime prime plus rho A u double dot. Now, let us add that there is a u dot term with some damping, let us say we will call it B u dot equal to 0. So, earlier we only had this, but now we have this extra term, this is our damping term, right. If we do that and go back and then see what happens. Okay. So, somewhere here let us add, okay, let us add the damping term. Okay. So, that will be our B u dot plus B u dot. That means that our integrand we wrote yeah, this is our f has that. Okay, that means that in the governing equation itself we will add the damping term over there. Okay, over there we add plus pu dot. Okay. So, what changes? We had said that this thing does not exist, right, that becomes 0, but now it will not be 0. Okay. Focus here, that is not 0, that will be because that multiplying lambda b will be there, minus lambda b by the minus sign. So, that kind of continues here. Okay. So, that minus lambda b will be there, and then here also minus lambda b is there. Sorry, in this case minus lambda b will be there, whereas here it will be plus lambda. That is what we added. We said that damping term, so not lambda, okay, that one second, this will be bu dot in the governing equation, it will be lambda b dot, because when I take this there is d by dt, so it will become lambda dot. So, there will be lambda dot b, then lambda dot b. Now, if you compare these two equations, they are not exactly the same, because over here it is a plus bu dot, whereas here it is minus bu dot. So, adjoint equation and the equilibrium equations are not exactly the same, because the damping term which depends on u dot has a plus sign in the governing equation, whereas minus sign in the adjoint equation. So, we cannot just solve, but we could solve it if we reverse the sequence, meaning that for solving equilibrium equation, that is to find u x t, we solve from 0 to capital T. Okay. When there is minus sign, I can switch the time, you know, for solving adjoint equation. Since we have minus sign, I cannot do the structure of the equilibrium equation. So, adjoint equation, I say I want to solve to find lambda x comma t, we solve from t to 0, that is backwards. Why is that important? Because when you look at the equation, adjoint equation, p plus lambda prime E a prime plus rho a lambda double dot minus lambda dot b equal to 0. Now, let us say that instead of the time t, let us actually have minus time with another variable defined tau. Tau is minus time, okay, backwards time. Backwards time. If you do that, how does this equation change? It changes, p does not change, and lambda prime E a prime has no dependence on the time. So, that also is just fine. Okay. But here lambda double dot, you have to take derivative twice. Now, we are doing with respect to tau, which has minus t. So, when you take two derivatives of tau, then it will become plus again. So, that remains plus, there will be rho a lambda double dot. Now, with respect to tau, this minus lambda dot will become plus lambda dot b equal to 0, because of what we have assumed that t is minus tau. So, over here what we have is p lambda prime E a prime prime plus rho a d square lambda by d tau square, and this one will be d lambda by d tau times b equal to 0. Tau goes from final time to 0. Now, if you look at this equation, this has exactly the same form as the governing equation. So, for us to solve, we can use the same Parent-Element routine to solve it rather than going backwards in time. Okay. This is what happens when there is a sequential time equal 0 happens, 1 second, 2 seconds, whatever, 2.5 seconds. When it goes like this, we go forward for equilibrium equation and then come backwards in negative time for adjoint. This is a characteristic of the adjoint method when there are these first order terms there. This can also happen in sequentially coupled multiphysics problems, which we will see after this into the next half of the lecture. Thank you.